talking about the RISC-V FDPIC in NOMMU.
Okay, so yeah, my name is Maciej. I work for Western Digital. It's actually my only second presentation from my university today, so it may be a little bit rough, but it's just, you know, Western Digital has been so welcoming such a welcoming environment for people to, and myself as well, to share knowledge and experience in person. So yeah, so here it goes. So this is quite an early stage of development. It's actually it's been only started a couple of weeks ago, and this is more of an ABI design at this point rather than an implementation. And I thought it would be good to give the details at this stage in the open source spirit of sharing early. So the thing is, we want to support Linux programs on NOMMU systems, and while technically it's possible already, like Damien has showed actually, but the problem is we want to conserve memory, and the only way of running programs right now is using the flat format, where essentially you have to allocate the same amount of memory as the program has, including the read-only and text segments, and which could potentially be shared between programs, and data, which is obviously specific to every program. So the problem here is that the ELF specifications have been made with virtual memory systems in mind, and they do not support what we require here, that is separating data from text, because there's only a single fixed value that any ELF image can be relocated by, and we're talking essentially DSOs, the dynamic shared objects here, which the position independent executables are a special case of. So also the RISC-V ELF psABI, PS stands for processor-specific ABI, uses PC relative addressing. So it relies on being able to calculate data addresses by adding a fixed value to the current PC. And there's no separate global pointer assigned to a register, unlike with some other architectures where there's actually a global pointer register. For your reference, here are pointers to the ELF GABI, the general ABI, which describes all the general principles for all the architectures, and the RISC-V psABI. So what are our design goals? So we need to modify the ABI so that we have a global pointer, which can then be used to access data. And we want to map text and data independently. The global pointer has to be specific to the individual module. So if we've got a single program loaded into memory and it's all dependent shared libraries, each of those libraries and the main executable will have separate global pointers assigned, and they have the global pointer has to be updated whenever a call is made between modules, because the modules themselves are not able to determine their own global pointer, which is because there is no relevance anymore to the PC as with existing RISC-V psABI. And also, the original value of the global pointer has to be restored when a call returns. This has to work for both direct and indirect calls, which has some implications which I show later on, and also for tail calls. The minor detail here is when you have a tail call, obviously you don't have to restore the global pointer. So if you've got a function that only has like a single tail call, there's no need to store the global pointer and restore it. And we're only going to support position-independent executables because if we were to support classic executables, the fixed position executables, we could only load one at a given position of memory, and we couldn't load another one. So this is essentially not going to happen. So just as an overview, here is how the general ELF ABI works. That we've got an ELF image which has a text segment and a data segment. They can actually be more than one of each of those. They do not have to be adjacent as shown here. It's just for simplicity. The key point here is we have an MMU available, and we can map the same image multiple times using essentially arbitrary load addresses. They can even be the same between different virtual mappings. And there's a single value that the ELF image is relocated by. This is called base address in the ELF GABI, and then all the segments map to pages in physical memory, and at this level we can do sharing of text pages. Data pages can be separate. Actually, there is a mechanism which is called copy on write, which allows data segments, well, pages of data be shared as long as nothing has been written to. So there can be some sharing here as well. However, the point is the data pages can be sort of naturally separated, and also we can maximize memory. We don't have to care about fragmentation because we can always insert a page just anywhere where there's no, which is unused essentially. So this is the classic position-independent code. In the case of no MMU systems, we have the flat model, which I mentioned before. It sort of works by coincidence. It's just nothing in the ELF spec forbids it. So as long as we can just relocate a program by a single value, the base address, we can still use the existing specification to support running programs on a non-MMU system. However, the problem is we have to make a full copy of the program every time it's loaded into our memory. And also, we have no paging available. So essentially, we use the full size of a program every time we load it of actual RAM. So in this picture here, actually, we have no space left for another copy of this program at all. So we can only run 2 copies. So with the FDPIC model, which is I'm going to describe soon, we can actually share the text segment between instances of a program. And there is no longer a correlation between the load address of data and the load address for text. And as you can see from this picture here, we could actually insert another data segment for the third copy of the program between the text segment and the data segment number 2. So how to implement this? We Oh, okay. So another explanation. This is about the PC relative addressing, as in the position-independent mapping, and the difference between a given location in the text segment and a given location in the data segment is always constant, because the relative position in the memory is always the same, and whether it's the virtual memory or the flat NOMMU mode. However, in the FDPIC mode, there is the difference between the same location in the text segment and the previously referred location in the data segment is no longer constant. So we need to have a separate pointer to address data in the data segment, which is where the GP relative addressing comes into a picture. So we define a separate global pointer register. Some other architectures actually have this already defined in the ABI. We have this reserved in the RISC-V psABI, which is the X3 register, and the ABI using the ABI name GP. It's not been used so far, however, so we will be using it for this ABI extension. The value of the global pointer cannot, as I previously noted, it cannot be determined from the PC. So it has to be calculated somehow and provided externally. So in the case of a Linux system, this is a map of the process is provided on the initial stack by the Linux kernel, and the initial startup code, which runs before the sort of proper user code executes, it can fetch the mapping in memory from the data structure on the kernel stack and extract the data load address and set up the GP register from that. We have 12-bit immediate offset available for ALU instructions for the addition and the memory access instructions. So we'll be offsetting the value in the GP by 2048, so that if we have a small data segment, we can address it directly off the GP register. As an optimization, it can be implemented, for example, as a Linux linker relaxation. It's not mandatory, but if it's reserved in the ABI, it's possible to do so. It may also help accessing the global offset table, more about which will be later. And with this arrangement, the offset from any data location within the data segment will be constant from the value of the global pointer. So we need to define new locations for that, for the static link, because the code example at the top shows the locations used for PC relative addressing. We'll have to have corresponding GP relative relocations. The code sequence is a bit longer, actually, because we have no instruction to add an upper part of an immediate to the GP register, so it has to be added explicitly, making the sequence 2 bytes longer. Yeah, so for external, that was for local symbols for local data. Yeah, so for external or preemptible data, let me just explain this shortly for those who are not familiar with that. external symbols are satisfied by when we have multiple dynamic load modules involved, then a symbol can be preempted by an instance from a different object. And essentially, the first module that defines a symbol, that provides a symbol definition, is the ultimate value of that symbol. If that's provided by the main executable, that it cannot be preempted really, because it always comes first in the dynamic load. However, if there's a definition in the shared library and also a definition in another shared library, or the main executable which comes first, the later definition will be preempted. So references from that module that provides the preempted symbol will actually refer to the value provided by the other module. That complicates things and requires an entry to be assigned in the so-called global offset table, where the address of the symbol, the ultimate address of the symbol, is stored. So the reference to this symbol has to be indirect. So again, we have a corresponding existing RISC-V psABI sequence to access the symbol using PC relative addressing of the global offset table. I forgot to mention that the percent operators are the assembly language operators which encode or request a specific relocation to be generated. However, the relocation on the topmost relocation, the topmost percent operator on the left-hand side is in italics because we don't actually have this operation in the assembler. So it's just shown here conceptually. Instead, the compiler at the moment uses a macro. It's sort of an assembly operation which expands to multiple instructions. However, the spirit of the operation is as showed here. So for procedure calls, we have three cases here to consider. For local calls, we can use the same code sequences as with ordinary PIC code, because we can the address of the function will be in the same module, so it can be reached with PC relative addressing, and there is no need to update the global pointer because we're going to be in the same module. For external calls, both the PC and the GP have to be updated when making a call. The values of the PC and the GP are only determined by the dynamic loader. So we need to have dynamic relocations to tell the dynamic loader where the values have to be inserted in the image of the program in the memory. We define a new structure, a new data structure called a function descriptor table, which is going to be created by the static linker, and the table will hold pairs of PC and GP. The PC will be the address of the function to call, and the GP will be the corresponding GP value for the module the function is in. So this is the FDT's global data will be allocated immediately following the GOT, which allows us to do this optimization that I mentioned before, and that if it's within the 12-bit range of the GP, then a single instruction can be used to access any location there. We have to create, well, strictly speaking, we want to create a procedure linkage table so that the calls, the setup for the call is done in the single place, and allowing the code proper to be smaller and also to simplify addressing. Yes, and okay. Then there are the indirect calls, which need to be made via also with the FDT. So they will serve as the pointers to the procedures. So the address of the FDT entry will be the pointer to the procedure, which will be used for pointer equality purposes as well, which solves the problem with protected symbols in the case where the protected symbol is a symbol which is always resolved locally, but it's also exported. So if another module requires this, it will be pulled from this one, but it will be never preempted. So all of this requires us to create an FDT entry for each of the module where a function is, for a function is either an external function is either defined or called, or whose address is taken for the purpose of making a call. And typically, we need to have a stack slot allocated in the functions prolog to preserve the GP across calls. So this is the structure of the function description table. Really, if I'm running short of time, so I try to do this quickly. So depending on the symbol scope, we have different dynamic relocation attached, so that either it determines whether a symbol has to be resolved for the relocation to be satisfied, or whether there's just a fixed offset added where a symbol is local and its address is taken. And your relocation is added to give the notion of the global pointer. It's going to be resolved to the value of the global pointer associated with a symbol by the dynamic loader. So this is how it's going to look like with the image of program in the memory. The text pointers are pointing at the functions in a text segment, and the global pointers point to the corresponding data segment. So here's the structure of the PLT, the procedure linkage table. We define new sequences to make calls via the PLT, both the direct call code sequence and the indirect call sequence. The PLT slots are 4 instructions each, which makes it 16 bytes. And the GP has to be reloaded after making a call, which is shown in the sequence on the left-hand side. Again, here's it's shown here how the flow of the pointers is when the code in PLT is executed. So when taking a function's address, we need to have a GOT entry created so that it can be filled with the ultimate pointer to the function. The pointer will be obviously a pointer to an FDT entry, as I previously mentioned, other than the function itself. And we use an R underscore RISC-V, RISC-V underscore 6432 relocations, so they are resolved at the load time. And we reserve the underscore RISC-V underscore FDT underscore namespace for symbols referring to these FDTs. So here's the how the address load instruction is going to. Yes. Okay, so I'll skip on the lazy binding then. We have got this sorted as well. The implementation, we're going to support in the GNU toolchain. GCC will support the FDPIC option and produce different code for this model. GAS will have to support this option as well because of the macros, where like the LA load address macro, which will have to look differently, like I showed before. BFDLD will support that as well, and we're going to update the dynamic loaders in the various C libraries. Most likely the uslibc will be the first one supported, then Mossel and the GNU C library. The Linux kernel part is already, I believe, it went. Okay, but it's on the way upstream, so yes. Well, the kernel part, we need it first, actually. We need to have the kernel part first. But anyway, well, we can work with a patch, no problem at all. So questions? Okay.
2 questions online.
Okay, so.